Example 2.22. Just as precise measurements are necessary in science, it is equally important to be able to make rough estimates of quantities using rudimentary ideas and common observations. Think of ways by which you can estimate the following. Where an estimate is difficult to obtain, try to get an upper bound on the quantity. A. The total mass of the rain-bearing clouds over India during the monsoon. B. The mass of an elephant. C. The wind speed during a storm. D. The number of strands of hair on your head. E. The number of air molecules in your classroom. Now see, first question, in that we want to calculate the total mass of rain-bearing clouds over India during the monsoon. So first of all, we have to calculate the area of India. So area of India, that is 3.3 into 10 raised to 12 meters square. Now in this particular area, suppose 100 centimeter rainfall takes place. It implies that the height of the water which fall on the surface area of India, that is equal to 1 meter. Now volume of the water, that is area into height. So mass of waterfall on India, that is mass, that is volume into density. So density of water, that is 10 raised to 3. Area of India, that is 3.3 into 10 raised to 12. Height of the water column which formed due to rain, that is 1 meter. So whatever is the mass of the waterfall, so we can say that is the mass of cloud over India during the monsoon. Clear to all of you? Now, mass of elephant. Suppose here a boat is placed in the water, and the boat sink in the water up to depth x1. Now if you want to measure the mass of elephant, then you have to place elephant in the boat. એટલે elephant ને તમે બોટની અંદર બેસાડો. Now boat will sink further in the water. Suppose now the boat sink in the water up to x2 meter height. It implies that due to elephant, the sink of the boat takes place, that is x2 minus x1. This is the additional sink. Okay. Now when we place elephant in the boat, at that time the volume of the water displaced, that is area of the surface of the boat into this height of the boat which sink in the water. So A into x2 minus x1, that is equal to the volume of water displaced. Now we know this thing. The buoyant force of water is balancing the weight of the elephant. So we can write the buoyant force of water, that is the weight of the displaced water, and it is balancing the weight of elephant. It implies that that is exactly equal to weight of elephant. Now weight of the displaced water, that is m0g, where m0, that is the mass of displaced water, and that is equal to weight of elephant, so that is mg. So gg is cancelled from both the side. So we can write mass of the displaced water, that is equal to mass of elephant. Now volume of the displaced water, that we calculated here, x into, sorry, a into x2 minus x1. So mass of elephant, that is mass of displaced water, so that is volume of the displaced water, A into x2 minus x1 into density of water. Clear to all of you?
Yeah.
Now wind speed of the storm. See, in that, what we have to do, we have to tie a balloon at a rigid support with the help of string with length 1 or 2 meter. Then after, during the storm, release it and then observe the position of the balloon under the effect of that wind. Now, here you have to take the measurement of the displacement of the balloon as well as the time interval taken by balloon to move from this vertically upward position to this inclined position. So now if we measure this distance and the time taken to displace from one position to another position, then you can calculate the wind speed V, that is d by t. Clear? Now fourth question, number of hair strains in your head. So here what you have to do, you have to consider 1 centimeter square area. Arbitrarily, you can take that 1 centimeter square area anywhere in your head. Then after, you have to calculate the number of strains in that 1 centimeter square area. Then after, you have to measure the total area of the head in which hair is there. Then multiply that total number of strains in 1 centimeter square with the total area, then you will get the total number of strains in the head. Practically, you can't do this thing. Clear? Now see, we want to calculate the number of molecules of air in the classroom. Yes, that we can calculate. Rough idea we want to take here. Now we know this thing. At STP, standard temperature and pressure, the volume of 1 mole air, that is 22.4 liter. So that is 22.4 into 10 raised to minus 3 meter cube. And that is the volume of 1 mole air. It implies that we know this thing. In 1 mole, the number of constituent particles, that is 6.02 into 10 raised to 23. So impliedly we can say this thing, in 22.4 into 10 raised to minus 3 meter cube, the total number of molecules of air, that is 6.02 into 10 raised to 23. Now very simple. You have to measure the volume of the room by measuring the length, breadth and height of the room. You can calculate the volume of the room. So now simple unitary method. in 22.4 into 10 raised to minus 3 meter cube, the total number of molecules, that is 6.02 into 10 raised to 23. Then in V meter cube, which is the volume of the room, how many molecules are there? So now simply you can calculate the number of molecules in room. Clear to all of you?